alle, guten Morgen. Heute ist 10. April 25. Das ist die Business Intelligence lecture. Good morning, everybody. Today we continue with our lecture series on deep learning by hand. The third part and last is about convolution, which is a methodology to extract information from Euclidean datasets. You see here an example of a picture of a color picture. We have performed a convolution and then we can extract the edges of the image. Okay, so here if we do zoom, we can see that we have the edges of the animal here. Okay, or the edges of the building and so on. Okay, so we learned today how to do that with pen and paper, and this is the backbone of convolutional neural networks that are used in deep learning. Okay, so background. Convolution is a technique, a method used in the image recognition, in the how do you say, in the data treatment of Euclidean domains. So in general, this can be, or examples could be images or videos and so on. In order to extract patterns like edges or colors from, or shapes, okay, from the data set. Okay, so convolution uses filters to extract the information. Or patterns, we can also say to extract the patterns. These filters are called kernels. Okay, kernels. So a kernel in this context is a tensor of weights that is used on the dataset recursively. Okay. So if we have our dataset, let's say we have this image. This is a color image. We make a little zoom on the, let's say, the nose of the Kuscheltier here. Okay. Let's make a little zoom on it. Okay. We advance to see here some interesting things. Okay. So the first thing that we see is that the thing has an orange in his mouth, and interestingly enough, we can recognize the face, the shape of the face of the here of our element. We can recognize an eye, we can recognize a part of the orange, the nose, right? And because we can recognize that because all the nose elements are together, all the orange elements are together, all the ear elements are together, and so on, right? So what we have here in reality is not a flat image. We have a cube. Okay. So we have 3 layers of pixels, 3 layers of elements that are put together in a cube format. Let me paint it pretty so that it can be better understood. So we have our cube, and why do I say this is a cube? Because we have 3 layers put together. Okay. First layer is going to be the channel red. Okay. This is going to be the red channel, and here we have a bunch of pixels. You see here the pixels, okay, here. Then we have the green channel. This is our green channel, RG, okay. And then we have the blue channel. So I'm sorry it takes a little bit time, but I think it's nice when later on the thing looks good. So we have our blue channel here. So, and each one of these channels has the pixels here superimposed. Okay, so we have here a little matrix. Of red. Pixels and the blues and the greens are the same, okay? So this here is like the pixel located here. Okay, it's going to be this, okay? So each pixel has 3 values in a color image. Okay. These values can attain 256 different value. Okay, so why 256? Because each channel R, G, and B, red, green, and blue, has 1 byte for each pixel. Okay, 1 byte equals 8 bits, and each bit can have 2 values, 0 or 1. Okay, so if you have 8 bits having each either 0 or 1, the combinations of 2 elements, 8 by 8 is like 2 to the potence of 8, that's 256. If we visualize it, we can say this is the pixel. Okay, so it's a number of 8. Okay, the 1, 2, 3, 4, 5. No, not 8. Now it's 8. So each one of these bits can be 0 or 1. And the combination of these bits give you the dimension, the number of possibilities. Okay? Any questions so far? So 3 values or 3 channels, okay? Better is 3 channels. These channels is better. So, no questions? Everything good? Good. So in an Euclidean data set, we can measure distance. Okay. In the example above, we know that there is an orange in the mouth of the thing because all the pixels of the orange are together. Okay. And this is important. If we cannot measure a distance, we cannot apply convolution like we are defining today. Okay? And we cannot use deep learning convolutional neural networks. We have to use other things. So what is, let's focus on the kernel. Input, kernel, or filter. Okay, let's focus on that. So that's the key to, so. The kernel has several properties. Kernels can have different shapes. Okay. Kernels filter information by adapting the input Euclidean dataset. So this gives us different types of kernels. you can use kernels for edge detection, like the one we have used in the example above. We can use kernels for blurring, to make an image non-recognizable. We can use kernels for sharpening an image. Okay. We can use the kernels for, there are many, okay? So we will see 3 or 4 examples, but there are like, I don't know, hundreds. So let's look at examples. For instance, for edge detection, we can use this kernel. Three by three. That has these values: 1, 0, -1, 0, 0, 0, -1, 0, and 1. So this is a 3 by 3 edge detection. Okay, kernel. Or we can use an attention kernel. An attention kernel would be like something like this. Zero, -1, 0, -1, 8, -1, 0, -1, 0. Okay? So this is a 3 by 3 attention kernel. You see the differences? Here, for the edge detection, we have the values in the edges. Here in the attention, we have the values in the center. Okay, the highest value will be the one in the middle, the one we're looking at. Okay. So these are just examples, but how does this work? Because this is very abstract. So let's make a real example with numbers, and then it will be, I think, very clear. Okay? Good. Imagine we have this data set. I have prepared it already. I have it somewhere here. Okay? So imagine we have this example. Okay? So we have this example in which we take the image and we take 3 channels, one red, one green, and one blue. Okay? And of course, these numbers are not the pixel numbers that we have in their original image, but just like we take a 4 by 4 pixels in the 3 channels. Then we defined a kernel, like an attention kernel. Given by this other, okay? This is going to be our attention kernel. You see that we have the biggest value is in the middle, and then we have minus numbers around that one, and then zeros the rest. Okay, so how does this convolution thing work? We need to define one concept still, the concept of stride. Okay, so how many pixels does the kernel move? Okay, so in this case we will say the stride is 1. You will see what this means in a second. Okay, 1 pixel. Sorry, 1 pixel. We remember we said that the convolution uses filters to extract information patterns, and these kernels navigate our domain to extract the information. Okay, so this navigation is done with the stride. But let's see what it means to let's see what it means to get the information. So we have our red channel. We take the red channel, okay, and we take our image. We take our red channel and we take our kernel. Okay? And now we say we are going to apply the convolution. And in order to do that, now please pay attention. We focus on this part. Okay? And now please pay attention. As I said, we multiply, we make a dot product. So the result of the convolution is going to be 1 multiplied by 0 plus 1 multiplied by minus 1 plus 0 multiplied by 0 plus 1 multiplied by minus 1 plus 2 multiplied by 4 plus 1 multiplied by minus 1 excuse me, plus 0 multiplied by 0 plus 1 multiplied by minus 1 plus 2 multiplied by 0. Okay, and this gives you, if we do that, minus 1 minus 1 is minus 2 plus 8, 6, minus 2 is 4. Okay, so the result of applying the first convolution, first time that you apply the convolution to this red filter with this window 3 by 3 is 4. Okay? Any questions how I did this? I try to be very slow. Okay. Yeah. Yes, we start in the left top part, yeah. And now we move it. Yep. So the next step is going to be to, like the colleague said, move it 1 pixel because the stride is 1, okay? We move it to 1 pixel to the right, okay? Here we do exactly the same. I will do this one also very slow. 1 multiplied by 0 plus 0 multiplied by minus 1 plus 2 multiplied by 0 plus 2 multiplied by minus 1 plus 1 multiplied by 4 plus 1 multiplied by minus 1 plus 1 multiplied by 0 plus 2 multiplied by minus 1 plus 1 multiplied by 0. If you do that, is 0 minus 1 multiplied by 2 is minus 2 plus 4 is 2 minus 1 is give you minus 1. So in total it gives you minus 1. Okay, so the next one is, now your intuition might tell you already. Now we move our convolutional window, that's how you call it. This window has the size of a kernel. 1 down, one pixel down, and to the left, okay? And here we do the same. No problem. We are multiplying the red square because we're doing the convolution. In mathematical terms, if you want to do it in math, okay, this is like this. We apply one function to another. So we apply first the first function g to x, and then we apply f to g of x. This is the way to do the convolution. I didn't want to bug you with math though, because people get lost, but this is what convolution means. The multiplication, this dot multiplication is what we do in the convolution. And we extract information there, so we are transforming this 4 by 4 in a 2 by 2 matrix. Okay? We transform the information. You will see the result now. So if we do this real quick again, 1 times 0 plus 2 times minus 1 plus 1 times 0 plus 1 times minus 1 plus 1 times 4 plus 2 times minus 1 plus 1 times 0 plus 0 times minus 1 plus 0 times 0. This gives you again 0. Okay, I mean you can, where, yeah, can be yep, yeah, you're right, 0 times minus 1. Thank you. So this gives you 0, and then the next and last is 2 times 0 plus 1 times minus 1 plus 1 times 0 plus 1 times minus 1 plus 4 times 2 plus minus 1 times 1 plus 0 times 0 plus 0 times minus 1 plus 0 times 1, and this gives you 7. Okay, so if you do that, we get a 7. So what we have done, we have transformed our 4 by 4 into a 2 by 2. Okay, so we have extracted information, relevant information, that we can pass on to the next layer. Okay, it's basically the same logic we did the other day. Instead of inserting, you remember we inserted one vector to our convolutional network. We are inserting a matrix right now. Okay, so a red channel of an image. Okay, so this is, we have done now the convolution. So now you know how to perform a convolution. In other words, we can repeat this for all the channels. We have the 3 channels here. Okay, we have our filter, which is an attention filter, a 3 by 3 attention filter. We pass it through the 3 by 3 attention filter, and what we get is, in the red channel, we get a 4 minus 1 0 7 matrix. For the green channel, we get different values again, and so on. Okay, so we have our red channel, we have our green channel, and we have our blue channel. And this is after one filter. We can make another filter and so on and so forth. Okay, so it's the blue. All right. So one might ask, what if we use a 2x2 filter instead of a 3x3 filter? Okay. So what if we use a 2x2 filter? What if? Okay. Then we get a different output. Okay. So this, let's say this is the solution, and if I ask you to perform a convolution in the exam, you need to do this. Okay. I mean, it's super simple math. Okay. I don't think this is very challenging. Okay. But what if we do a 2x2 filter? Let's say now we try a 2x2 filter. And one of the things I'm trying is to demystify artificial intelligence. Okay, so I'm trying to with these lectures, I'm trying for you to lose your fear to artificial intelligence, because this is super simple math that a 10-year-old kid can do. Okay, so the math you need to perform artificial intelligence, at least in the early stages, is not very difficult, just to understand the principles. And this is, I think this is very important for your future professional development. Okay, do start learning artificial intelligence in any way you can. Okay, and this is just an introduction course for business intelligence, but I mean, understand that I cannot do much more than this. But I want you to lose your fear, because most of the times we don't start something because we think this is out of our reach. Okay, so you don't go and talk to the pretty girl in the disco because you think, oh no, that she's too pretty for me. Okay, so I don't go talk to her. I don't want to be. But the fact of the matter is that she wants to be talked to. So if you go and talk to her and you're nice, and she might even like you. Okay, so if you don't try, you don't have any chance. So just do it. Okay, just try to talk to the girl in the disco. Do it. Doesn't matter. Just the worst step is or the most difficult step is to start. I guess that's what I'm trying to convey here. So if we have I'll say it in German because it's important. Ich versuche hier, dass ihr die Angst verliert, okay, zu KI oder diese Methoden, weil die Mathe, die man hier macht, kann ein Viertklässler machen, okay, also es ist nicht Rocket Science oder so. Und ich möchte, dass ihr euch traut, weil wenn ihr euch traut, dann habt ihr eine Chance. Wenn ihr euch nicht traut, dann habt ihr gar keine Chance. Okay? Das war ein bisschen die Idee. So stellt euch vor, just imagine we have now a 2x2 kernel. What do we do? And stride equals 1. So here I do it again. 2 times 1 plus 0 times 1 plus minus 1 times 1 plus 1 times 2. This is 4 minus 1 is 3. Okay. So the first number we get is going to be 3. We perform the same thing again, but with a stride here. Okay. And then we say 2 times 1 plus 0 times 0 plus minus 1 times 2 plus 1 times 1. This is going to be 1, okay? And if you do again, you get, let's do 2 or 3 examples more. One more stride. Two, 0, minus 1, 1. Then we have 2 times 0 plus 2 times 0 minus 1 times 1 plus 1 times 1. This gives you 0. Okay. Now we perform another yet. So we bring our kernel 1 pixel down. And this gives you 2 times 1 plus 0 times 2 minus 1 times 0 plus 1 times 1. This is going to be 3 again. So if you continue, you get here a 5, 1, minus 1, 2, and 5. Okay. And this is the output of the kernel. And one might say, hey, but with a smaller kernel, you get more information. This is weird. No, it's totally normal. Why? Because with a smaller kernel, you have more what? Resolution. Okay? You have more resolution. You're looking at more detail. Okay? That's why you're getting a bigger output. Does it make sense? Yes, Nicolas, yes, okay. Everybody's saying yes. Okay, so now you know how to perform deep learning. Convolution. And this, combined with what we saw the other day with the feed forward and back propagation, is 80% of deep learning. Okay? So now you can perform deep learning on your, let's say, piece of paper. Of course, it takes a lot of time. And that's why it was not developed until we had computational power to do it. But these concepts are there since 1960. So no rocket science, nothing that we cannot do with a piece of paper. All right, so Any questions so far? No questions? Okay, so one might say, all right, when you do a convolution, let's say we have our example, and you apply, let's say, an attention kernel to that set of pixels. Okay, so this is a 3x3 attention kernel. One might say, yeah, you are multiplying this and this and this and this by zeros. So you're losing information. You're not paying attention to this one here. You're losing it forever. Right? Makes sense? This is what we lost that. We lost that information here when we did that multiplication. You remember here we have 1 times 0 here. Okay? So we lost that information. And this is sometimes not good. Sometimes you want that information because it might be relevant, okay? So what do we do? Anybody have an idea? We might lose information in the edges. Of an image with certain kernels. For instance, our attention kernel. You see why we lose the information, right? Yes or no? We just multiply it by 0, so we cannot use it. So if I multiply you by 0, then you're gone. Okay. So what do we do? Any idea? No idea? Well, we do something called padding. Okay. Padding is about adding zeros around the image. Okay, so we say padding p equals 1 means we add a line of zeros around the image. So we're not adding any information there. we're just adding zeros. What for? For the case that when we have this, and with a padding of 1, we transform this into this. Sorry. Okay. We have added a bunch of zeros around our data. Okay? This allows us to to keep all the information of the image after convolution. Okay, so let's see how this works. Is this understandable that we add zeros around? Just put 0, 0, 0, 0, 0, 0, 0, just a line of zeros. It's like, you know, when you put a pretty picture on the wall, you put a frame, okay? You want the frame to be, I mean, the frame is not part of the picture, but helps you get the image prettier or highlighted, okay? That's pretty much like that. All right. So what do? Let's get this example again, convoluted. Now we perform convolution with stride equal 2 and padding equal 1. Okay, so now stride is going to be 2. All right, so let's get the domain. No, because I want you to see the example with stride number 2. Yeah, I want you to see many examples, so I do the stride number 2 now. We can do stride. No. Good question. So let's say, yeah, so we get the thing here going. This is our filter, okay, just like we had it. So the guy that just talked, what's your name? David. Good. Where should I put my window? Tell me. Here. Is that correct? No, you tell me. Is it correct? Yeah, it's correct. Very good. So we do the multiplication. Okay, this is just the first row is multiplying by zeros. I don't put it. We start with 4 times 1 plus minus 1 times 1 plus 1 times minus 1 plus 2 times 0. This is going to give you a 2. Okay. So David, stay with me, please. Don't go too far. Where is the next one? Remember, stride is 2. What? 2 to the right. So I start here, right? Very good. Yeah, so you got it. Very good. So David got it. Everybody is in the same page, or we need to explain again? We moved here 2 steps, okay? So stride is 2, so 2 pixels. Are we cool? Yeah? Okay, if we're not cool, just make your microphone on and then ask, okay? No problem at all. This is just very normal that you don't get it the first time. It's very normal. It's actually not normal that you get it the first time. First time I saw this, I didn't get it. Okay, so you multiply the first row with zeros, just forget about it. Then 1 times minus 1 plus 4 times 0 plus 2 times 0 plus minus 1 times, no, sorry. 0 times, I'm making a mistake here, I think. Making a mistake, going too fast. Too fast ain't good. So 4 times 0 plus 2 times minus 1. And then 0 times 2 plus minus 1 times 1 plus 1 times 0. So this is minus 3 minus 4, I guess. So we start copying for our result. We have 2 and then minus 4. So again, David, come back to me here. What's the next step? Where do I put my window? So yeah. You're out. So we don't do out. We need to stay in the window, okay? No, you cannot move 1 because we have stride 2. So you always move 2. You're a 2-step frog, okay? You jump 2 steps. So your frog just jumps every time 2 steps, okay? Good. Yeah, very good intuition. Exactly. So we start right there, right? Good intuition. Perfect. So we are here, okay? So this is our new window. And yeah, so we do just the same, just like, you know, like your little brother can do it, who is 8-year-old, okay? Just 0 times 0 plus 1 times minus 1 plus 2 times 0. One question that people ask. What if I do a mistake here in the exam and I just mismatch? And okay, if you make a mistake in the calculation, not big deal, okay? But make sure that you visualize everything and you explain everything so that I know that you understand what the fuck you're doing, okay? So if you explain what you're doing and I see that you understand it, if then you miss one number, it's not a big deal. I miss myself the numbers sometimes because I'm talking and writing and looking at if there's questions and stuff. So of course it's not perfect, so you don't get the full point, but it's not a big deal. Okay, is it fair? I think it's fair. Good. So um, 0 times 0 plus 1 times minus 1 plus 0 times 0. If we do that, we get a minus 2. And then, David, stay with me again. We just finish our example. So what's the next step? Very good. So that's very good intuition. We now move 2 to the right, so we would be like around here, making sure that we get all the information in place. Okay? Actually, we're not getting all the information. We're losing something on the right, so we would need to do a padding of 2. But just to explain the concept, it's more than enough here. So we do again 2 times 0, 1 times minus 1 plus 1 times 0 plus 2 times minus 1 plus 2 times 4 plus 2 times minus 1 plus 0 times 0 plus 0 times minus 1 plus 1 times 0 equals 7 at some point, I think, if we add it all up. So what we're getting here is minus 2 and then 7. All right. That cool? Okay. Any questions? No? Good. Then stop the video here. That is, of course, you need to understand it. Here I import the necessary background programs or packages. Here I create an input matrix, which is our pixels. This is a grayscale image. The images are, or the pixels are close to 0, then they are black or blackish. If they are close to 256, they are whitish or white, more clear. Okay. So we define a kernel, which is in this case is an attention edge detection kernel. We apply the convolution function, which is basically what we just did. Okay, so we apply a 3x3 kernel to a 2-dimensional matrix, step by step. First we define the matrix shape, then we define the kernel shape. The output shape will be like this. Okay, you can look at it. Just that's why we got different sizes, different outputs for the kernel 3x3 and for the kernel 2x2. And then we slide the kernel over the matrix. So we go with a stride 1. Okay, I guess this is a stride 1. And we move it along the kernel. We move it along. We move the kernel along the image. We apply the convolution, and then we visualize the output. So what we get from this is, if we apply, it's like we have the image. We apply the first kernel okay, and we get this number, which is very high, so it's going to be white. The next, we move our window, we apply the kernel, and we get a very negative number, so it's going to be black, and so on. Okay, so you see the first pixel is a white, okay? The second is a black, then we get another black, and then we get a gray, okay? So the third is going to be negative, so it's going to be black. And the last one is going to be like above 0, like around in the middle. So if we now say we want, because we're having an attention kernel, this number is going to be crucial. So let's change this from 200 to 10. So it's going to become black. Now what we get here, see, remember we had here a black number, a white pixel on the top left corner of the after applying the kernel, and here we have a black instead of a white as before. Okay, so this is the way a little bit you can play with this. If we put it like it was, then this white is crucial, so we get another white. So what happens now if we want some padding? Well, we can add some padding very easily if we add some zeros. Okay, I'll just do it live for you. And then we get some zeros around the image, up and down. I guess it's 3, 5 numbers. I made 6, so no. So we need 6. We need zeros also on the top and on the left. So here, what we're doing is we're adding some padding of 1. And by adding some padding of 1, what we're doing is, see, we have like a ring of black ring, and now we are not losing so many information when we do our attention kernel. Okay, and this is the effect of padding, I guess. Is this understandable? Yep. I guess if some of you, I'm assuming you're in the 6th semester, you know how to deal with Pythons a little bit. Okay, so if somebody has problems with this, let me know. I mean, this is not a Python class, so that's why I fly over it. But it's also good to know that we can do whatever we do with the pen and paper, we can do it with code. Okay. So now we do some color detection. Okay, so we have a kernel that does color detection. So it's going to take one image that is now in color, and it's going to detect if there is red or blue in the convolution. Okay. So in order to do that, we define our edge kernel. We define our color detection, okay, and this is a color detection kernel. This is not only for red, but we focus it on the red, but it's the same for the blue. It's just focusing on the middle, in the middle. So we describe one image. In order to do so, we describe each pixel with the 3 values R, G, and B. Okay, so this is going to be red because it's full value of red and 0 on the rest. Depending on how we combine these values, we get different. So let's say if I say the first pixel is 255, 255, it's going to be a mixture between red and green. So we get yellow. Okay? If we say, I'm talking about the top left. So if we say instead of red and green, we mix red and blue, we might get something like rosa. Okay, something like purple thing. Okay, so same thing. We're just changing here the values. You can play with it to make it more pretty. You can add some padding. you can do whatever you want. Okay, so we apply the convolution function just as above. The red channels are this. So this is like moving into this cube, three-dimensional cube we said. This is the first channel, the second channel, the third channel. And then we apply the convolution to detect red and blue. And we show it, okay, we print it. And what we see here is that we are detecting red in the first convolution. We are detecting some red. We are not detecting blue. That's why we see here some red dot. In the second convolution, we're detecting blue, okay? Only on the second and on the fourth, okay? So that's why we see here the dark blue and the rest is 0, okay? So this is basically the little code that I wanted to share with you. Any questions?